The fundamental distinction between cloud computing and edge computing lies in where data processing occurs. Cloud computing centralizes computational resources in distant data centers, while edge computing distributes processing power to the network periphery, closer to where data originates. Understanding this architectural divergence reveals why these paradigms serve different purposes in modern digital infrastructure. Cloud computing represents a centralized model where computational resources, storage, and applications reside in large-scale data centers operated by providers such as Amazon Web Services, Microsoft Azure, or Google Cloud Platform. These facilities house thousands of servers interconnected through high-speed networks, offering virtually unlimited scalability. When a user requests a service, their data travels across the internet to these remote data centers, where powerful machines process the information before returning results to the end user. The architecture of cloud computing leverages economies of scale. By consolidating resources in massive facilities, providers achieve remarkable efficiency in power consumption, cooling, and maintenance. This centralization enables sophisticated redundancy mechanisms, with data replicated across multiple geographic locations to ensure reliability. The cloud model operates on a shared infrastructure principle, where multiple tenants utilize the same physical hardware through virtualization technologies, optimizing resource utilization. Edge computing fundamentally inverts this paradigm by positioning computational resources at the network edge, in close proximity to data sources and end users. Rather than transmitting information to distant data centers, edge computing processes data locally on devices, gateways, or micro data centers situated near where the data is generated. This architectural approach emerged from the recognition that certain applications cannot tolerate the latency inherent in round-trip communication with centralized cloud facilities. The edge computing infrastructure consists of distributed nodes that perform pre-processing, filtering, and analysis before selectively transmitting relevant information to the cloud. These edge nodes range from industrial sensors with embedded processors to local servers in retail locations or cellular base stations equipped with computational capabilities. The distributed nature of edge computing creates a hierarchical processing model, where immediate decisions occur locally while aggregate analysis happens centrally. Latency represents the most critical differentiator between these paradigms. Cloud computing introduces inherent delays as data traverses network infrastructure, typically ranging from 50 to several hundred milliseconds depending on geographic distance and network conditions. For many applications, this latency remains imperceptible and acceptable. However, edge computing reduces response times to single-digit milliseconds by eliminating long-distance data transmission, making it indispensable for latency-sensitive applications. Bandwidth considerations further distinguish these approaches. Cloud computing requires substantial network capacity to transmit raw data from endpoints to data centers and back. As the number of connected devices proliferates, this model can create network congestion and incur significant data transmission costs. Edge computing mitigates bandwidth demands by processing data locally and transmitting only essential information, such as aggregated insights or anomaly alerts, to centralized systems. The security and privacy implications of each model differ substantially. Cloud computing concentrates sensitive data in centralized repositories, creating high-value targets for malicious actors, while simultaneously enabling sophisticated security measures and expert oversight. Edge computing distributes data across numerous locations, reducing the impact of individual breaches but increasing the attack surface and complicating security management. Additionally, processing data locally can address regulatory requirements, mandating that certain information remain within specific geographic boundaries. Autonomous vehicles exemplify applications where edge computing proves essential. These vehicles generate massive volumes of sensor data requiring instantaneous processing to make split-second navigation decisions. Transmitting this information to distant cloud servers for analysis would introduce unacceptable delays, potentially resulting in catastrophic consequences. Instead, onboard edge computing systems process sensor inputs in real time, while the cloud handles less time-critical functions such as route optimization and software updates. Industrial manufacturing demonstrates another domain where edge computing delivers substantial advantages. Factory equipment equipped with edge processors can detect anomalies, adjust parameters, and prevent failures within milliseconds, maintaining production continuity. Simultaneously, these systems aggregate performance data and transmit it to cloud platforms for long-term trend analysis, predictive maintenance scheduling, and cross-facility optimization. Cloud computing excels in scenarios requiring massive computational power, extensive data storage, or complex analytics that benefit from centralized processing. Machine learning model training, big data analytics, and enterprise resource planning systems leverage the cloud's virtually unlimited scalability and sophisticated infrastructure. Applications without stringent latency requirements or those handling non-sensitive data often find cloud computing more cost-effective and manageable. The relationship between cloud and edge computing is increasingly symbiotic rather than competitive. Hybrid architectures combine both paradigms, with edge devices handling immediate processing while leveraging cloud resources for intensive computation, long-term storage, and centralized management. This complementary approach allows organizations to optimize for both responsiveness and scalability, deploying computational resources where they provide maximum value. Cost structures differ significantly between these models. Cloud computing operates on a consumption-based pricing model, where organizations pay for resources utilized, avoiding substantial upfront infrastructure investments. Edge computing requires investment in distributed hardware and ongoing maintenance across numerous locations, though it can reduce long-term operational costs by minimizing bandwidth consumption and cloud service fees. The optimal economic choice depends on specific use case requirements and scale. The distinction between cloud computing and edge computing ultimately reflects different solutions to the challenge of processing increasingly vast quantities of data generated by connected devices. Cloud computing offers centralized power, scalability, and simplified management, while edge computing provides low latency, reduced bandwidth requirements, and localized processing. Modern digital infrastructure increasingly incorporates both paradigms, strategically distributing computational workloads to achieve optimal performance, cost efficiency, and user experience.